So now I want to do an example that's not in your book. And what we're going to do is we're going to predict what that NMR spectrum should look like for the molecule. And so the molecule that we're going to look at right now is this one. And I'm going to draw in all the hydrogens. And I suggest you do the same thing. Drawing my lone pairs of electrons. So we're going to start off with that molecule, but first I want to show you a model of this. Okay, so this is exactly what we've got up here drawn on the board. We've got our benzene ring shown here with our 4 hydrogens that are attached. We've got our sp2 hybridized carbon of the ketone. The red atom here indicates the oxygen. We've got our methyl group here, our CH3. We've got our oxygen down here at the bottom with our 2 lone pairs and our CH3 just like we have shown here. So the first thing that we need to ask how many signals would we expect out of this particular molecule? I expect to see 4 signals. Let me show you why. We have the CH3, which is clearly different from this CH3. Why is it different? Because this is attached to an sp2 hybridized carbon. This one is directly attached to an oxygen. They are different CH3 groups. They are going to appear at different locations on the NMR spectrum. So even though they're CH3s, they're both going to appear at different positions. We're not worried about where they're going to appear yet. We're just trying to identify the different signals. These 2 hydrogens are identical. And these 2 hydrogens are identical. So I expect to see 4 different signals. Now, the question you may be asking is, why are these 2 hydrogens the same, and why are these 2 hydrogens the same? Well, if you look at the model as we have it drawn on the board, so just flat and planar, you would predict that this hydrogen is actually different from this hydrogen because this hydrogen sees this oxygen, whereas this hydrogen, quote unquote, can see this methyl group, and that's different. However, remember that this bond right here is a single bond, and we can get free rotation, just like we can get free rotation down here. And so on the NMR time scale that the experiment is occurring, this is spinning very, very fast. And so this proton and this proton basically see the same thing. And so I like to actually represent it where we have the groups going like this. And what you can see right through the molecule is a plane of symmetry. Okay, and so this plane of symmetry through here makes this proton and this proton identical. However, notice there's no plane of symmetry through here. There's nothing that makes this proton equal to that proton, and so those are different groups. So we have these 2 that are the same, and we have these 2 that are the same, this one, and this one, and that gives us our 4 signals. The second question that we need to ask is, where would we expect them? Where would we expect those to be on the spectrum? And I mean this in a very broad sense. We would expect these 2 signals that are on the benzene ring to be greater than 5. So 2 of those signals are going to be above 5, somewhere between 5 and 10. And we would expect these 2 methyl groups to be below 5, based on the rules that we looked at when we were looking at splitting it at 5. So we've kind of got an idea of what the spectrum should look like. And then we need to ask, what would we expect the splitting to look like? What would the splitting pattern be? Well, let's look at this particular methyl group to start with. This methyl group has 0 neighbors. These 3 hydrogens are all the same, but it's connected to a carbon that has absolutely no hydrogens attached to it. There are no neighbors, so this is going to be a singlet. Just one straight line. This CH3 is similar to this one in that it's attached to an oxygen which doesn't have any hydrogens on it, so there's no neighboring protons. So it too is going to appear as a singlet. So I expect two singlets. And here, since these are the same, they don't split one another. And they're going to give rise to the same signal. But this one has one neighbor. So it's going to appear as a doublet. And this one has one neighbor. So I expect to see two doublets. And with this information, we should then be able to kind of draw, with the aid of some tables, what the spectrum would look like. So let's go ahead and do that. And so we're going to have our NMR spectrum, 0 to 10. The intensity is going to be on the y-axis, of course. This is our delta, or parts per million. We expect to see two signals on upfield of 5. And we're going to see one of those at about 3.9-ish. And we're going to see another one at about 2.5. And they're going to integrate to the same amount, 3. Then on the left-hand side of 5, or downfield of 5, we expect to see two doublets, somewhere between 7 and 8. So I'm going to just say this is going to be about 8 right here. We're going to have a doublet, and we're going to have another doublet somewhere pretty close to 7. And now we have to figure out what is what. That's kind of what we would expect this to look like. The integration here is going to be 2 to 2 to 3 to 3. And again, that gives us the relative number of protons that we have. In this case, I'm using the exact number of protons, but it could have been 1 to 1 to 1.5 to 1.5. That's the same ratio. Okay. So which one of these doublets belongs to this set of protons, and which doublet belongs to this set of protons? Well, we have to look at the electron withdrawing groups. And you might be tempted to predict that the oxygen is a very strong electron withdrawing group and that would be closer to these, pulling those further downfield. However, oxygen's also a donator of electrons by resonance because it's got the lone pair of electrons. So these protons are actually, I'm going to call these A, are the furthest upfield, and B, being attached closer to this electron withdrawing carbonyl, are going to be a little further downfield. Okay. So we have A and B. And now we have to make a decision between these two singlets. They are here, and it turns out that we'll call this one C and D. D is further downfield than C because this carbon is directly attached to the electronegative oxygen, so it's pulling these further downfield. There's no way for this to resonance push electrons into this methyl group. You can't get a resonance structure for that, like we can get a resonance structure going this way for this H. So these are actually going to appear a little further downfield. These are going to appear a little further upfield. But these aren't going to appear at 1. They're going to appear somewhere around 2.5 because they are connected to this electron withdrawing carbonyl group. Okay? They're just not as far downfield as the methyl protons attached directly to the oxygen. So that's it for part A. We are going to start again with part B in the next video, talking about the carbon NMR, how to interpret carbon NMR, and then give you a strategy for the overall way of taking all of this data that you're going to have in lab and actually putting together a real molecule.